In the course of our learning, it is important we understand what happens when any of the three components is connected in an AC circuit. We need to know the behavior of voltage and current when each of them, for instance, the resistor, the inductor, the capacitor, is connected in an AC circuit. And that is what we're going to learn today. So before we delve into all these details, let me remind you to subscribe. Come on. Thumbs up, come on. And then put on the bell button for constant notification. Don't forget to share with your friends, network, and students. My returning subscribers, thank you so much. My new subscribers, you guys are amazing. Come on. Belong to this family. Let's go. When a resistor is connected in an AC circuit, we need to understand the behavior of voltage and current. That's our concern. Alright? What happens, especially when there is a potential difference across it? So when a resistor is connected in an AC circuit, the vibrating voltage and the currents are in phase, meaning they flow, they move in the same step. The current does not lead the voltage, neither the voltage lead the current. Both work or flow in step. That is what happens when a resistor is connected in an AC circuit. And that is the reason why the factor phi is equal to 0, because there is no lead, neither is there any lag. That's the first thing we need to understand here. Both currents and voltage are in phase under the condition that the circuit contains only a resistor. Take notes. Then the second circuit has to do with an inductor. When an inductor is connected, how does voltage behave? And at the same time, how does current behave? When an inductor is connected, the inductive voltage and the inductive current fall out of phase. They are out of phase by a certain factor, pi over 2 radians. That's what happens here. Okay, let's see. And that pi over 2 radians is as a result of what is leading now is voltage. The inductive voltage is one step ahead. What does that mean? Both the maximum, 0, and minimum values of the inductive voltage have one step ahead of the inductive current. This is interesting. Meaning also that the inductive currents correspondingly lag behind, allowing the inductive voltage to lead. That is what happens when an inductor is connected in an AC circuit. Take notes and remember the factor, and that is why you can see the inductive voltage is leading, and that's why we have plus in this equation or relation. That is why we have minus, because the current lags in this condition. Alright, having said that, let's see what happens here. What happens here is very simple as well. Of course, when a capacitor is connected, both the capacitive voltage and the capacitive currents are out of phase. I repeat, both are out of phase, meaning they don't flow or operate in the same step. Under this condition, the good news is the current leads. The current leads the voltage. The voltage lags behind in this condition. The reason is this: the maximum value, the maximum, 0, and minimum values of current are one step ahead, while correspondingly all these for voltage one step behind. And that is why current leads here. when a capacitor is connected. Take notes. Alright? Now we have understood what happens when a resistor is connected, when an inductor is connected, and then correspondingly what happens when a capacitor is connected. We now have these three components connected together. But before we move into explaining this, we must understand that it is time for us to subscribe, thumbs up, and then push on the bell button for constant notification. Don't forget, there are students that need this. There are parents that need this for the children. Push it to them, encourage them to learn. Come on. And what happens here is very simple. When we have the inductive reactance greater than the capacitive reactance, the factor phi is positive. This factor becomes positive. Check it. And what is leading here? Current leads. Is that clear? This is interesting. And then conversely, when this inductive reactance is less than the capacitive reactance, of course the factor phi is negative. That is it. And if we have that, if we understand that properly, we can now calculate the resultant voltage of the entire components in the AC circuits. And then to do that, we have this. A Pythagoras theorem method can be applied here. And that is V squared is equal to VR squared plus VL minus VC all squared. If we take simplification of this, we will arrive at a concrete answer. Now, if we do that, what about the first difference? How do we now calculate the first difference? Phi. Tan phi is equal to VL minus VC over VR. If we have the values and substitute accordingly, making phi the subject, we will be able to calculate that angle. And then if we don't want to use this, there is also an alternative where we are provided with the inductive reactance and the capacitive reactance over the resistance offered by the resistor in the circuits. If we carefully substitute this and then apply simple arithmetic operation in solving them, we will come up with something tangible. And we'll be happy. Learning is very simple, all right? So I want us to enjoy it. Thank you so much for watching up to this point. It's done. It's done. Look at it. If there is anything that I've said which is not clear, put it in the comment section and I will address it. All right? If you have found value in what I've discussed so far, give me some thumbs up. Put it in comment section, share with your friends and networks, students. Also, remember to put on the bell button so that each time content like this are uploaded, you will be notified promptly. I'm signing out. See you there.